We're going to go over positive transcriptional control in repressible operons and inducible operons. Alright, so remember with positive transcriptional control, the regulatory protein we're going to be using is the activator protein. So that's what we're going to be using to turn the operon on and off. And remember that the definition for a repressible operon is it's always going to be turned on unless there's too much end product. So if I ask you on the test to define what a repressible operon is, that's the definition that I'm looking for. Okay, and then part B of the question that I might ask on the test would be if this repressible operon is under positive transcription control, how is it turned on? Okay, so if we're using positive transcriptional control, we need to think about where the activator protein would be if it's turned on. So the activator protein is going to bind to the activator binding site on the DNA, and that actually helps the RNA polymerase bind to the promoter. So when the activator protein is bound to the activator binding site, that helps the RNA polymerase bind to the promoter, and then it can go ahead and do transcription, transcribe the genes in the operon, and then those can be made into the proteins and the operon will be turned on. Okay, and then part C of the question would ask, how would this operon be turned off? So how we want to turn it off would be if there's too much end product around. Okay, so maybe we made too much of whatever the end product is. So we need to figure out how to get the activator protein off of the activator binding site. So how that happens is if we've got too much of our end product around, then the end product will bind to the activator protein, and that'll cause the activator protein to change shape, and that'll make it fall off the activator binding site. And now that the activator protein is no longer bound to the activator binding site, RNA polymerase is no longer able to bind to the promoter, so there won't be any transcription, and that's going to turn the operon off, okay, which is what you want because you don't want to keep making the end product because you've got too much. And then our last scenario is using positive transcriptional control to turn an inducible operon on and off. So again, we're going to be using an activator protein. That'll be our regulatory protein to turn this operon on and off. But now we're going to be working with our inducible operon. And if I ask you to define that on the test, an inducible operon is going to be turned off unless the substrate's present. Okay, so if I put this scenario on the test, the next thing I would ask after asking you to define what an inducible operon is I would ask you, how would this inducible operon be turned off if it's under positive transcriptional control? So we've got to think about where the activator protein would be if this operon is turned off. So if it's turned off, the activator protein would not be bound to the activator binding site. And then that means that the RNA polymerase cannot bind to the promoter because the activator protein is not around to help it. So there won't be any transcription. And that'll turn this inducible operon off. Okay, and then the next question I would ask would be, how would we turn this inducible operon on? And we're going to turn this on if our substrate is present. So how would we get the activator protein to bind to the activator binding site? Is that if our substrate is present, it will bind to the activator protein, and that'll change the activator protein's shape and allow it to bind to the activator binding site. And now that the activator protein is bound to the activator binding site, RNA polymerase can bind to the promoter. And now it can go ahead and transcribe the DNA. And now we've turned on our operon. So that's how we would turn it on. Okay, so that would be our last scenario that I could put on the test. Okay, and then another operon just to know would be the tryptophan or TrpOperon. And this operon is a repressible operon that's under negative transcriptional control. It contains 5 structural genes. A structural gene is just a gene that codes for a protein. And these genes will code for enzymes that are used to make the amino acid tryptophan. So let's just look at this operon. So if we're using negative transcriptional control to turn this operon on and off, the regulatory protein we're going to be using would be a repressor protein. And then just the definition of a repressible operon. Remember that these are always going to be turned on unless there's too much end product. And the end product in this case would be tryptophan. Okay, so if we want to draw this repressible operon, this TrpOperon turned on, we've got to think about where a repressor protein would be. And the repressor protein would need to be off of the operator for this TrpOperon to be turned on. And if a repressor protein is off of the operator, that means that our RNA polymerase can bind to the promoter. And we can go ahead and do transcription. So that would be the TrpOperon turned on. Okay, but if we've ended up making too much end product, we made too much tryptophan, we need to turn this TrpOperon off. So we need to change the shape of our repressor protein to get it to bind to the operator. So how this is going to happen is that our end product, tryptophan, will bind to the repressor protein, and that'll change the shape of the repressor protein and allow it to bind to the operator. And now the repressor protein is in the way, so RNA polymerase can't bind to the promoter. And there's going to be no transcription. And so that'll turn our operon off, which is good because we don't want to make any more tryptophan because we've got too much of it. Okay, and the other operon to know would be the LacOperon. Lac just stands for lactose. And this operon is going to code for some proteins that are going to be used to break down lactose as a food source. Okay, and this is what the LacOperon looks like. So here's our 3 genes that are going to code for genes that are going to be used to break down lactose. And we've also got a transport protein that's also coded for to bring lactose into the bacterial cell. Okay, so this does code for proteins to break down lactose as a food source, but the bacteria do have a food source that is their favorite food that they'd rather eat first over the lactose. So it's just like if I had a plate of food in front of me and there's some dark chocolate on the plate and some broccoli, I would much rather eat the dark chocolate first because that's my favorite food. So I'd eat that first, and if I'm still hungry, then I'd eat the broccoli next. Okay, so this is exactly what the bacteria are doing. So their favorite food would be glucose. And you can see why that's their favorite food, because they actually can get more energy out of glucose than they can out of the lactose. And so you can see here on this bottom graph that they would actually eat the glucose first. And you can see there's a little bit of a delay here as they turn the LacOperon on, and then they'll eat the lactose. Okay, so they'll eat their favorite food first, they'll eat the dark chocolate, and then once that's gone, they'll eat the broccoli, they'll eat the lactose. Okay. So the LacOperon is an inducible operon, which just means that it's going to be turned off unless the substrate's present. And our substrate is lactose. Okay, so we're not going to turn the LacOperon on unless lactose is present. Okay, so there's actually going to be 2 switches for the LacOperon. Okay, and it's just because they like to eat their favorite food first, the glucose, and then they'll eat the lactose. Okay, so we're going to have both negative and positive transcriptional control on the LacOperon. Okay, so with negative transcriptional control, we're going to use our repressor protein. And with the negative transcriptional control, this switch is going to look at and say, hey, we're only going to turn the LacOperon on if lactose is present. So if the substrate is present. Oops. Okay, and then our other switch, the positive transcriptional control, we're going to use our activator protein. And this one is going to look at the glucose, and it's going to say only turn on the LacOperon if there's no glucose present. Okay, so you're only going to turn on the LacOperon if lactose is present and there's no glucose. All right, so your favorite food's gone, your glucose is gone, and you've only got lactose left. You've got to meet those two conditions to turn the LacOperon on. So that's why they're using both the repressor protein and the activator protein. Okay, so let's just take LacOperon out, and let's look at our repressor protein first. So we're going to be turning this on only if lactose is present, okay? And we're going to be using the repressor protein to check for that. So normally this would be turned off. The repressor protein would be bound to the operator unless lactose is present. So if lactose is present, it will bind to that repressor protein. And it'll change the shape of the repressor protein. Let's see, we'll give a different color for. So our substrate are lactose. Okay, binds to the repressor protein, changes its shape, and that makes it fall off the operator. Okay. All right, and then our other switch is looking at whether glucose is around or not. So we're only going to turn this on if there's no glucose. So we can't use glucose to bind to the activator protein because there's no glucose around. So we've got to use another signal to get our activator protein to bind to this activator binding site. So we're going to use cyclic AMP, which is a cell messenger inside the cell, which actually increases when there's no glucose. So this just means that, hey, there's no glucose around. So cyclic AMP will bind to the activator protein when there's no glucose, and that'll change the activator's protein shape, and that'll allow it to bind to the activator binding site. And once the activator protein binds the activator binding site, then RNA polymerase can bind to the promoter. And since the repressor protein is off the operator, we can go ahead and do transcription. And that will turn the LacOperon on. Okay, I'm not going to make you draw this on the test, but all you need to know about the LacOperon is when we turn it on. So we're going to turn this on when lactose is present and there's no glucose. Okay, so that's when we're going to turn it on. So lactose has to be present and there's no glucose. All right. Okay, and then the last thing we're going to talk about, so what we've been talking about with the repressor protein, the activator protein, we've been talking about whether we're going to turn on transcription or not, whether we start transcription or transcription initiation and make the messenger RNA. But what if we've already made the messenger RNA and then we decide, oh, wait a minute, we actually don't need to make those proteins? And so we can actually block translation. So these microRNAs, what they're going to be doing is they're going to block translation. So this is just another way to turn these operons on and off, or genes on and off, because we also use use these in our cells too. Okay, so these microRNAs will block translation. Okay, so they call them microRNAs because they're really small. And here's how they work. So let's say that this green messenger RNA is the messenger RNA your cell's already made, and then the cell decides, hey, wait a minute, we actually don't want to translate this and make the proteins. So to block translation, you will actually transcribe these microRNA genes, and then the microRNA has a sequence that will line up with that messenger RNA that you decide that, hey, we don't want to translate that. And when the microRNA binds to the messenger RNA, it creates this double-stranded RNA, which we generally don't have double-stranded RNA in our cells. And so our cells look at that and say, hey, that's not supposed to be here. We don't have double-stranded RNA. And so enzymes come along and destroy the RNA. And once the RNA is destroyed, you can't translate it. And so it won't get made into proteins. Okay, so that will prevent those genes from being made into proteins, and you'll turn off those genes.